first of all, thank you very much for inviting me to give a talk in this conference. Welcome to St. Louis. I actually live in St. Louis, and I'm going to talk about the Vera C. Rubin Observatory, the legacy survey of space and time. I'm currently affiliated with the Department of Astrophysical Sciences of Princeton University, but in about a week and a half, I'll start working for the SLAC National Accelerator Laboratory, which is a Department of Energy laboratory managed by Stanford University. And that's also part of this project. So in this talk, I'm going to give a brief overview of the 4 components of the Rubin Observatory, which is the telescope inside, the camera that we built, the data management system, and the education and public outreach system. And I'm going to mention the science themes behind this galaxy survey that we want to do. In particular, I'm going to focus on cosmology, which is what I do, observational cosmology. And we're going to talk a little bit about who Vera Rubin was, and dark matter, dark energy, and stuff like that. So I wanted to start with the mission statement of the Rubin Observatory. So the mission of this observatory is to build a well-understood system that will produce an unprecedented astronomical data set for studies of the deep and dynamic universe, make the data widely accessible to a diverse community of scientists, and engage the public to explore the universe with us. And I wanted to read this because there's a lot to unpack there. It's telling us that we haven't done this before. It's an unprecedented system at this scale. And we want to do a studies of what we call the deep universe. We want to do cosmology. You want to integrate and look at very, very faint galaxies. At the same time, we want to do what we call the dynamic universe, which is all the stuff that changes on the sky on different time scales. So these 2 things are going to be at odds, and it's going to be challenging to put together the technical requirements to make these scientific goals. In addition to this, we want to involve all the astronomical community in the United States and in Chile and in the world. Chile is where the telescope is going to be. And a very important point of this is that since the beginning of the project, the education and public outreach component was there from the beginning, which usually in astronomy, EPO is important, everybody loves astronomy, but then you don't give money to it, and then yeah, that's it. No, it's an afterthought. So the Rubin Observatory is going to conduct a survey, a galaxy survey, that is called the Legacy Survey of Space and Time. It's going to last for 10 years, and if we put it in one sentence, given by one of the intellectual architects of this project, Tony Tyson, we can say we can put an optical camera on an 8-meter telescope with a field of view of the size of 40 full moons, and then we're going to use this camera to take 1,000 photographs of every area of the visible sky for 10 years. So you can more or less picture that next time you look at the full moon, you're going to think of the large field of view that this camera is going to have. And I said this is something unprecedented. The LSST, the Legacy Survey of Space and Time, is going to be the first project of the Rubin Observatory, and is going to give us the next step in astronomy. So here I'm putting pictures of space telescopes. This is not the Rubin Observatory. You might recognize the JWST, and then there are other telescopes called the Euclid Space Telescope and the NASA Nancy Grace Roman Space Telescope on the right. And these are telescopes that are going to complement what the Rubin Observatory is going to do. But the real power of a telescope is given by the power of by the product of the field of view and the size of the mirror that it has. So in terms of that number that is called étendue or grasp, the Rubin Observatory is actually the best of all. And it's going to give us a catalog of about 20 million stars and 20 billion galaxies with an excellent catalog of properties, positions, and brightness. So basically, we can say that we're going to have a digital and color movie of the universe. So just for historical purposes, some of you may know, or may not know, but this project was called the Large Synoptic Survey Telescope in the past for historical reasons, but then the National Science Foundation, who's providing part of the funding of this project, decided to name it in honor of Vera C. Rubin, due to in recognition of her contributions to the study of dark matter and her advocacy for the equal treatment and representation of women in science. So just to be a little bit more specifics, the LSST, the objectives of the LSST are to obtain a catalog of millions of images. We're going to take about 6 million images with about 200 detectors. I'm going to explain a little bit more about these detectors later. We're going to calibrate these images, which is actually what I work on, something called instrument signature removal, a little bit technical, but it's basically cleaning all the images from whatever the detector is giving you, and it's not the signal. Then we need to produce the catalogs of the detected objects, and then we also need to make that amount of data available to the users, which, as I said, is the scientific community, not only astronomers, other people with technical expertises, and also the general public. So the ultimate deliverable of the LSST is not just building this telescope, but it's also the fully reduced science-ready data and the software as well, which is all open science. From the historical point of view, this idea came back in the 2000. It was initially called the Dark Matter Telescope. And in 2010, it was recognized by the National Academy of Sciences as the most important ground-based astronomy project that the United States should focus on. So every 10 years in the United States, the astronomical community gets together and decide what they're going to spend the money on, and then they produce a report with the National Academy of Sciences that is read by Congress, by NASA, by people who have money, and then they say, okay, this is the project that we should build. We're going to build this telescope in the northern part of Chile, or more or less the center. Chile is very long. It's called Cerro Pachón. There are different reasons why we chose to build an optical telescope there. The most important one is clear and is semi-desertic. When you want to build an optical telescope, you want a place where it's not humid. And there are also other political reasons, and also they already have the land there to build other telescopes. This is just a picture of the site and a picture of one of the astrophotography of the type of skies that you can get from there. So the first component of this project is the telescope on site. This is a subsystem that, of course, includes the telescope itself, the buildings and facilities, and everything that you need in order to support the operations of this Rubin Observatory. So on the right-hand side, you see inside that funky-looking building, and there you see we have all sorts of technical equipment here. This is, usually you don't have that type of facilities in an astronomical observatory. Another funny and interesting picture that you see on the lower left is actually the tunnel that goes to the mountain. It has a certain width. So the maximum diameter of the telescope was also constrained by what you can fit in that tunnel. So that was about 8.4 meters. So of course you want to build a bigger telescope, but at the same time you have these types of practical constraints. These are more pictures of the telescope mount assembly, and then some pictures from the top of the telescope. That's also already finalized construction. Then the next thing I wanted to talk about is the camera. So this is a very cool camera. It's called the Elasticity Camera. Very original names that we have in astronomy. And it's the largest digital camera ever built. So that's really amazing. So it has dimensions of about 1.5 meters by 3 meters, and it weighs about what a car weighs. So here we have it in the imperial system units, just to make a comparison. One funny order of magnitude or Fermi problem that a colleague of mine did is how many corgis I could fit in the camera. And I was like, oh, all right. I don't know what assumptions, spherical corgis, in physics we call it spherical cos, so I guess she did the calculation, and she said that she didn't harm any corgis. So here, this is a picture of where the camera was built, which is at SLAC National Accelerator Laboratory in California. As I said, it's the highest resolution digital camera in the world, and they actually got a Guinness World Record to prove it, so yeah. And somebody did the calculation and said you would be able to spot a golf ball on the moon while standing on Earth, to give you an idea of the type of resolution that you have with this camera. As I said, it's the largest digital camera ever built for astronomy. And also it has the fastest data readout time of any camera built so far, because we need to, in order to attain one of those scientific objectives of looking at everything that changes in the sky, you need to actually read the camera very fast and then go to the next part of the sky and so on and so forth. In order to do cosmology, you need to look at the very, very fainter galaxies of the universe, so you need to look at things for 10 years. So that's what we call deep, wide, and fast. This is a schematic of the camera on the left. The lens, the first lens, I believe is also the largest lens in the world or something like that. And this is, let's see if this goes. Yeah, it's moving. So this is a schematic of the type of filters that you put in front of the camera. So what's happening here is that when astronomy is an observational science, you cannot go to the lab and just play with your galaxies, so that'd be cool. So what you look at is the images of the galaxies, and in a great, perfect world in which we had all the resources in the world, we would split the light of every galaxy that we get, and we do a spectroscopy, right? So for every wavelength, then you get a certain amount of power, and then that tells you about the chemical composition of the galaxy, it tells you about the distance of the galaxy from us, it tells you about the rotation velocities of the stars. But that if we did that for the billions of galaxies that we wanted to do, then we would never finish and we would need a lot of money. So we do something what is called photometry. This is the type of information that a galaxy survey like this actually gathers, which is just basically taking pictures of objects, of celestial objects in different filters, and you can still see by the difference in how they look like in different wavelengths. You can still infer all these properties that I told you. In particular for cosmology, the distance is very important. So that's a little bit of the explanation of the type of photometrical survey that we're doing. This is again another picture in the SLAC National Accelerator Laboratory, and this is a picture of the primary and tertiary mirror in Arizona, in the University of Arizona. I forget the name of the lab, Richard something. But you can see in the center one of the higher ups. I guess when you're a higher up, you get to see it on the expensive mirror. One of them is Tony Tyson that I have mentioned that came up with the idea many years ago. And then you also see that they're all men. That's also another problem in astronomy that we need to talk about, and that's something that Vera Rubin also was very aware of and asked us to do better. This is actual pictures of the detectors. So I do a lot of work with something that is called gravitational lensing, that I'm going to tell you more about that. And then I studied the detectors and how these detectors, the errors from these detectors are going to propagate into the signal that I want to measure. These detectors are called charge-coupled devices. They're digital detectors. And they revolutionized astronomy. So back in the time when they invented the photographic plates, that revolutionized astronomy, of course. Then in the 60s, people invented the digital detectors called the charge-coupled devices. They were perfected in the 70s at the Jet Propulsion Laboratory in California, and then people started to build these large cameras in the 90s and in the past two decades, these large wide field of view CCD cameras. So here we're going to have 21 RAFs, or electric towers, I call them sometimes. Each one of them has 9 detectors, so we're going to have a total of 189 detectors to make this big field of view that I talked about. These are more detailed pictures of the camera at SLAC, already assembled. We haven't shipped the camera to Chile just yet, but we're planning to do so next year. These are, again, more pretty pictures of the actual electronic graphs coming into the focal plane. And then one more picture of the guide sensors. On the corners, you have sensors out of the plane to do guiding and alignment. When they finished the camera, they did a press release at SLAC, and then they put a picture of Vera Rubin with a pinhole camera, not with the actual lenses. And the LSST camera, as I said, is the largest digital camera in the world that we have built so far, and is the culmination of certain other types of cameras that we have built in the past decades. The one you see in the top left is called the Hyper Supreme camera that is in Hawaii, that it has also a lot of CCDs, but it doesn't have as many as the one of the LSST camera. And the one on the right I also wanted to talk about because I did my PhD in this project, which is called the Dark Energy Survey, that it has about 500 million pixels camera still. It gives us an idea, these precursor surveys, of what to expect with the LSST. So I wanted to show this animation of actual data. And this is from the dark energy camera. This is a telescope close to where the Rubin Observatory is being built. And you can see the size of the moon. You always kind of compare with the size of the moon. In the dark energy camera, you can put about like 3 full moons across that you compare with that with the more or less 7 full moons in diameter that you can put in the Elasticity Camera. But when you do this type of galaxy surveys, this is how you do it, by tiling the sky little by little and then coming back to it and doing it in different filters. And then with the dark energy survey, we only had money to do a little part of the sky. It's not little, this is actually big. This is like, it's 5,000 square degrees to the 18,000 square degrees that we're gonna see from Chile. Then we're talking about something different. But we already have these precursor projects that are gonna tell us a little bit about what to expect. Then we have the data management system. So far I have worked for the data management system, and as I said, the software is one of the most challenging aspects of the Rubin Observatory. We're gonna produce about 20 terabytes of data, and that should be per night, and that should be processed and stored each night. So you take all this data in Chile, close to a town called La Serena. So the telescope is about 50 kilometers or something up the mountain. Then you send the data to La Serena, then it goes to Brazil, and then it goes to, it used to come here to Illinois, the National Center of Supercomputing Applications, but now it's gonna go to SLAC. And we also have partners in France and the United Kingdom, so the data also is going to go there. And I wanted to show this image. This is an image of what we call the commissioning camera. It has the same type of sensors that we have in the Elasticity camera. This is like a one raft. You see the 9 CCDs, and each CCD has 16 segments because you want to read the charge quickly. So one way of doing that is just to split in the detector in many areas. But you can see a picture of somebody in the lab, and then you can see all this horrible stuff on top of it. So that's the job of the instrument signature removal pipeline, to get rid of that. And then you see like things like rings, and again, I wrote a paper of what those rings are, like, oh, the electric field in the CCD, you have the photon producing the charge with the photoelectric effect, and actually that's moving my charge from one pixel to the other pixel, so that's bad, because then I think that the galaxy was in one place, but it's actually in another place. And that's also bad because I thought that the galaxy had this brightness, but it has another brightness, so that's not good for the science that we want to do. And here I'm saying it very colloquially, but I'm talking about like 1% effect and something very, very tiny. That for a project like this is actually going to be important, because a project like this, we're in what we call the systematic limited regime. For all our lives in astronomy, we did not have objects. It was just, we could only see a little part of the sky, and then we have like 3 galaxies, and from that we need to draw a line and say, this is cosmology, this is the Milky Way. Now, the statistical problem is gonna be solved. We're gonna have billions of galaxies, and now we're gonna be in the regime in which, if we want to make progress, we need to pay attention to all these systematic errors that do not go down when you do an statistical average. This is another slide just to make an emphasis on that, and saying that the existing tools and methods are not going to scale up to what we want to do. And we're going to have this huge statistical database, about 100 petabytes. For each of the 40 billion objects, there are going to be about 1,000 measurements, I said, and then each one with a few dozen parameters. So then we end up with a tens of thousand dimensional parameter space. So we have the challenge of characterizing what we know, the norm patterns. We need to classify new populations that we might find. We need to discover unusual objects, the unknown unknowns, and this is one of the most exciting aspects of this type of projects. We don't know what we're gonna find. And a lot of people put a lot of effort in developing new techniques that we haven't used in previous projects, using techniques from other fields, like computer science, using techniques from artificial intelligence and machine learning, of course. And as I mentioned before, one important component of the Rubin Observatory is education and public outreach. We want to do it in a systematic way in which people can do what is called citizen science or community science, in which members, non-subject matter experts of the community can contribute to the scientific effort that we're going through. And I actually, when I moved to St. Louis, I didn't have a job, and I found an astronomer colleague in Edwardsville, Illinois, and I had the chance to work on this type of community science projects from the scientific point of view. So it's something very valuable, and as I said, it is very important that the Rubin Observatory is, from the beginning, putting a lot of emphasis on education and public outreach. For this other part of the talk, I wanted to mention the 4 science drivers of LSST. These are the main drivers that what we want to do with it. But as I said, we're going to be able to do much more than this. So one of the science goals is cosmology. Cosmology is by definition, is the study of the universe as a whole. We want to learn about the composition of the universe, something called dark matter and dark energy that I'm going to tell you in detail later. But we also want to know about our own solar system. We're going to do different inventory of the different populations of the solar system, all those asteroids that are between Mars and Jupiter, or all this stuff that is beyond Neptune, which are called trans-Neptunian objects. All these things are actually remnants from the early history of the universe, and we want to make an inventory of these objects. And in addition, we have this population of objects called near-Earth objects, and that by definition they're close to the Earth, but a subset of them are what we call potentially hazardous loose objects or asteroids, well, things that could kill us, basically. So that's also an important thing that we're going to catalog with the LSST. Actually, in 2005, the Congress mandated NASA to find 90% of the objects that could actually pose a threat to the Earth that are more than 140 meters or kilometers. Well, sorry for the order of magnitude slip in my mind, but the point is that there is a threshold that even at that threshold is going to be very dangerous for us. So the LSST is actually going to help fulfill this mandate. We also want to know about the Milky Way, the structure formation, our own galaxy, the origin of our own galaxy. And we want to explore, as I said, what we call the transient sky. We have a lot of variable stars. We have exploding stars called supernovae. We have stuff called active galactic nuclei, black holes. Or we're going to discover new types of transients. So we've never done that in the past. You have these different subsets of the astronomical community, and they build their own project to do each type of science, because it's really hard to actually do a single project that is going to make the whole astronomical community happy. So I wanted to focus on the cosmology side a little bit, and I wanted to talk about first Vera Rubin. So Dr. Rubin was born in Philly, born and raised in the 1928. She moved to DC afterwards when she was 10 years old, and she went to Vassar College, and then the high school teacher told her, "Oh, you'll be fine as long as you stay away from the sciences." Like, of course. And then, but then Rubin's like, "No, what are you talking about?" She had a role model called Maria Mitchell, the first American astronomer who got a PhD that she taught at Vassar. So Rubin thought, well, of course I can also be there, an astronomer. Why not? So then she wanted to go to grad school. She got accepted to Harvard, but then she said she decided to follow her husband. And then probably she was happy to do so, but at the same time, you have all these other pressures that you can measure systematically, that women are more pressured to follow their partners than the other way around. So and that's something that still happens. So she ended up going to Cornell, which I guess is not bad. She wanted to go to Princeton, but they told her, like, no, you're a woman, so you cannot study here. So then she went to Georgetown to get her PhD. And I think she stayed afterwards about 10 years or so. And then let me tell you about why, the type of contributions that she did for astronomy. So back in the time, in the 30s, there was this Swiss guy called Fritz Zwicky, or Zwicky, pardon my Swiss German. And he was working at Caltech, and then he was looking at clusters of galaxies and the galaxies, everything goes around, everything rotates in the universe, so the clusters of galaxies are orbiting their common center of mass. By applying physics to that, you can see how fast the galaxy clusters are, the galaxies are rotating in the galaxy cluster, and you can infer the amount of mass that must be causing that movement. And then he did the calculations that actually you would need more mass that you can actually see in order to explain those dynamical movements. And he called those, that missing mass, he called it dark matter because it didn't absorb or emit electromagnetic radiation. Then Vera Rubin in the 70s, I believe, look at different scales, look at the scales of galaxies, and then she looked at the velocity of the rotations of galaxies around the center of the stars, around the center of the galaxy. You would expect, like in the solar system, that as you get farther, for example, in the solar system, as you get farther from the sun, the orbital velocity of the planets goes down, and that's Newtonian mechanics, that's Keplerian mechanics. But they actually did not find that. They found what we call the flattening of the curves. By using different type of techniques, you found out that the velocity of the stars as a function of the radius from the center of the galaxy did not diminish. You can explain these observations by invoking the hypothesis of a new type of matter that we don't know about that does not absorb or emit electromagnetic radiation, but it has gravity. So the current accepted model of cosmology says that we have a certain type of dark matter that is called cold dark matter, and every galaxy has a halo of this dark matter surrounding the galaxy. The picture on the right is actually an actual picture of two clusters colliding. And by different techniques, you can see the gas of the galaxies going, the shock, like when you have a bullet go through an apple, for example, you can see the gas in the center. And then on the right, using another technique that I'm going to talk about, you can know about the distribution of dark matter. So you can actually see the separation of the type of normal matter and dark matter. And the current paradigm is telling us that galaxies and clusters of galaxies, they all live in what we call the cosmic web. So this is a simulation in which every bright point is a halo of dark matter. They're joined by filaments. You have voids in between. And the spatial scale of this type of picture is about hundreds of millions of light years. So megaparsecs is the unit that we use in astronomy, but you can think of it of hundreds of millions of light years, or you can think of like, oh, this is very big, because even a light year, I don't even remember in terms of kilometers how it is, but it's the distance that light travels in 1 year. Then we have some funny picture from JPL about the dark matter and for Halloween. But then I just told you that you cannot see dark matter by definition. So how can you see dark matter? So we can use a technique called gravitational lensing, which is basically the bending of light by any distribution of matter or energy in the universe. This is an idea that comes from Albert Einstein, from the theory of general relativity of Albert Einstein from 1915. This is the best theory that we have to understand gravity and that we use in cosmology. And it tells us that if you have something like the sun or a galaxy, and then you have a source in the background, and you're observing the light from that source, that light is going to get bent when it passes close to this mass distribution. So it's called lensing because it is analogous to the lensing of light, for example, from a glass. If you have a candle and your source, and then you have a glass of wine, and then you can see the effect of gravitational lensing, which is similar to what you actually observe in galaxies. You can see that you can form a ring depending on the geometry between the observer, the lens, and the source. You can get a full ring, which is called the Einstein Ring. You can see multiple images. You can see a magnified image. And these are actual pictures of this phenomenon from using the Hubble Space Telescope. So this is something that is real that we can measure. That blue arc, which is almost the ring, is a galaxy that is way in the background and is being lensed by a cluster of galaxies that is in the foreground. These are pictures, again, of a cluster of galaxies. You need to squint a little bit, but the one on the left is from the Hubble Space Telescope. The one on the right is the one that recently they showed to Biden when the JWST had the first images. And you can, if you squint a little bit, you can see these arcs of galaxies being lensed and distorted in a tangential way around the center of the cluster of galaxies. And this is a happy face using from gravitational lensing. So, you know, the human condition that we want to see faces everywhere, so it's right here with gravitational lensing again. But then with gravitational lensing, we can know where dark matter is in the universe. So the name of the game is to get all these hundreds of millions of galaxies at different types, at different distances. The further you look back, then the more you're looking back in time, because the speed of light is finite. So actually you can reconstruct the history of the universe by looking at galaxies that are very far away. And then again, you can make this cosmic web and this filamentary web and know about the distribution of galaxies and how it evolves in the history of the universe. The current cosmological model and the current theory is what is called the hot Big Bang theory, plus the inflation. Well, there are some. So the Big Bang is not the name of a show. No, it's the actual scientific theory that told us that despite its name, it wasn't an explosion. It's always a misnomer. It's like impressionism, and like somebody wanted to make fun of Big Bang, so they say, Big Bang. But it's actually that in the past, the universe was very, very hot, very, very dense, and it just started expanding and cooling down. So that's basically the idea of the Big Bang cosmology. And the evolution of the universe is going to depend on the contents of the universe. As I said, the best theory that we have to understand cosmology is general theory, the theory of general relativity, that tells us that space-time is curved by any distribution of matter. So the universe is going to evolve depending on the contents of what it has. It's not going to be the same if we have a universe that doesn't have any galaxies, that if it has more dark matter or more something else called dark energy. So the universe started expanding, and this was already like a big discovery back in the 1920s. Actually, Einstein himself, after he wrote the equations of general relativity, he showed that the universe should be expanding, but he didn't believe it. He actually put a mathematical term to have a universe that should be static, because that was the belief of the time. But then in the 20s, it was observed in California, in Mount Wilson, that the galaxies actually are going farther and farther away with distance. And this provided empirical evidence in favor of this idea of a universe that is expanding. Another empirical evidence is something called the cosmic microwave background, which is a signal that you can see all across the sky. It's something that you can see on the right. The picture on the right is a projection of the sphere on the whole sky, and those differences in colors are different in temperature, but these differences are actually very, very tiny. It's like 1 part in 1,000, and this is consistent with this leftover radiation from the Big Bang. So people were expecting that a universe that is expanding and has galaxies, due to the gravity of galaxies, the universe should be slowing down. It came as a surprise in 1998, when people actually found out that the universe is expanding faster and faster with time. So it's like if you have a rock and then you throw it to the sky and then it slows down, and then out of nowhere it starts speeding up. So people and scientists were thinking, there must be some sort of force or something else that we don't know what it is that is causing this accelerated expansion of the universe. So it's accelerated because it's changing the velocity with time. So of course, people were like, what are you talking about? Like, this is not actually, this cannot be what it is. But then after this happened in 1998, and in the past 20 or 30 years, 25, then it has been actually confirmed with other experiments that the best hypothesis or the best model to explain what we observe in the universe includes a model that has dark matter, about 25% of dark matter of everything that's in the universe. There is 70% of everything that is in the universe that is dark energy, and the rest, like you and I and the chairs and everything, then the galaxies and the stars, that's only 5%. So it sounds crazy, but it is the model that explains the observations. And then we apply Occam's razor, and that's the model that we have. And it's a model that has been tested. And people with this type of galaxy surveys, people want to look at the data, which is the cosmic microwave background. And you can think of the cosmic microwave background of the baby universe. And then you apply your mathematical model, your cosmological model, which is called lambda CDM. Lambda stands for a type of dark energy called dark matter. You apply that mathematical model, and then you forward it in time, and then you obtain something that you should observe that you can compare with what the distribution of galaxies that you see nowadays. So you compare the baby universe with the adult universe, and then you see if your cosmological model makes sense or not. And this is by studying the evolution of dark matter through gravitational lensing and other techniques throughout the history of the universe. So this is one of the main motivations for doing the Lsst, as I said, and I wanted to go a little bit more in detail of that because it's part of mainly of what I'm doing, of what I do in my research. This is just a rendering of the current status of the Rubin Observatory. It was supposed to be finished a couple of years ago, but because of the current pandemic, then things had to stop. But we're making progress, and maybe let's see if we can look at a video of the construction of the Rubin Observatory just for fun. So you blow up the mountain. My wife is an ecologist, and she was not happy about that. Like, it's like, then you start building all this in Chile. As I said, one of the advantages is that you already have the infrastructure to bring all the materials and bring everything. The land belonged to something that is called the Association of Universities for Research in Astronomy, which is something based in the United States. So they already have the land to make this telescope. They have an agreement with the Chilean government in which Chile is an equal partner in the project as well. And then we have other international partners, but Chile is one of the main ones, of course. And it's getting there. I'm very excited. I might go there next year. We'll see, because now we need to get things going. It's what is called commissioning. There's going to be a lot of work. And I'm very excited and looking forward to that. Yeah, so I think it's already not. I'll finish it. But I want to finish with a reminder of Vera Rubin and what she stood for. She's actually, she never got the Nobel Prize in physics. Many people thought that she should have gotten it. But naming the observatory after her is a way of honoring her legacy. And it's not only about science, but also honoring the hardships that she went through and how we need to do better. So in particular, she experienced something as a minority, as a woman, but today we know that many people of color, many minorities in astronomy. Here she was talking to the Berkeley people who were graduating and told them we only have 3 black colleagues with PhDs in the United States. You need to do better. So Vera Rubin also stood for that and how we need to do science in a better way. And then we also need to think about those issues as well. And with that, I'm going to finish. And you can follow me on Twitter, or you can follow my podcast in Spanish if you want to practice your Spanish listening skills. Thank you. I don't think I have time for questions, I guess, technically, but feel free to email me or talk to me, or I'm in the Slack message if you want more details about anything. Thank you very much.